Hi, everybody. This is Robert Hodges, and I will be the presenter today at our webinar called Size Matters, Best Practices for Trillion Row Datasets in ClickHouse. Before I get started, I'd like to just do a quick confirmation. Thank you very much, the person who answered that the sound is good. Let me know if there are any concerns about that, uh, and we can dive in. Let me tell you just a few things about this webinar that will help you as you're listening. First of all, it's being recorded. You probably noticed that when you joined. And let me just double check the recording is on. Great. So we'll send you links to the recording as well as the slides after this. Second thing, we have time for questions on this, and there's a couple ways you can put them in. We're pretty informal about this. You can either put them into the Q&A box, which is available off the little webinar control panel bar that Zoom shows. Put them in there, or you can just type them into the chat. It's not a really big deal. I'm watching both of them. And if there are things that are relevant to what we're talking about, I will talk about them as we go along. Otherwise, there should be some time at the end, like at least 10 minutes to cover questions. Good. I hope that's clear. With that, what I'd like to do is go ahead and dive in, and I'll do some short introductions here. So I'm Robert Hodges. My day job is I'm the CEO of Altinity, but for this webinar and for the purposes of this kind of presentation, I'm a database person. I've been working on databases for almost 40 years, starting with something called M204. I've worked with about 20 or more databases, some of them for many years, other ones like DB2 for one day. And I just like databases. The experience that I'll be describing in this webinar comes from all of Altinity. We have a number of very, very talented engineers. When we add up all their experience, it runs into centuries. And they have helped people build and operate very large data sets on ClickHouse, and in some cases they've also operated these clusters themselves. So we have a lot of experience in this area, and what this talk does is collect some of the nuggets from that we'd like to share from you. And then finally, a little bit about Altinity. So we're an enterprise provider for ClickHouse. We help people build real-time analytic applications on top of ClickHouse through both software, including Altinity.cloud and things like the Altinity Kubernetes operator for ClickHouse. That's the thing that enables ClickHouse to run cloud natively on Kubernetes. And then we have support. So we basically provide everything that you need to get started and become productive quickly on ClickHouse and stay that way. All right, that's enough marketing. Let's get to the meat of this. And what I'd like to do is begin by covering some of the basics. It is possible that there are people on this call that have never heard of ClickHouse. So let's just have a quick review of what ClickHouse is. It's a SQL data warehouse. So a data warehouse is a database that is designed to answer questions about large amounts of data very quickly. So what it means is our focus is on reading data very efficiently. ClickHouse Characteristics, it understands SQL. So like most data warehouses these days, it's very portable. It runs on everything from bare metal to the cloud. It runs great in Kubernetes. It has what's called a shared nothing architecture, which means that, and this is a traditional data warehouse architecture that's been present for many years, but basically ClickHouse for the most part operates as a process with attached storage, and then those processes are connected over a network. So if you're putting them together in a cluster, all they need is a network connection between them. Like most data warehouses, it stores data in columns. This is much more efficient. We'll dig into this a little bit, but basically it means that when you're doing selects, you only pay to read the rows that you're interested in. If you have 100 rows and you read, or excuse me, 100 columns and you read 3, you will only need to do I/O on those 3 columns and not the rest of the data. It also uses, like many data warehouses, both parallel and vectorized execution. So parallel in the sense that we're very good at parallelizing a query across cores, across CPUs, and then across nodes in a network that comprise a ClickHouse cluster. Vectorized execution means that we treat data as arrays and try and push them into the CPU as efficiently as possible. So reading them directly through memory, ideally hoping to match the structure of the L1, L2, L3 cache, and then of course, where possible, to use SIMD instructions, single instruction, multiple data. So these are all characteristics of important characteristics of modern data warehouses. Scales to petabytes, and it's open source, and it's extremely popular. So ClickHouse is probably the largest analytic project now on GitHub. It's bigger than Elasticsearch, has more contributors, and is growing very rapidly. Okay, so that's a lot of marketing about ClickHouse itself. What I'd like to do is actually do some quick demos before we get into this talk, just to show you what ClickHouse can actually do. So let's go ahead and just one second. I need to find my. Here we go. So what I'm going to show you here is some demo queries that are running on ClickHouse that's running in our cloud. So this is just so you know, if you're the kind of person who cares about this sort of thing, it's a C5 9x large instance. It has about 1.3, 1.4 terabytes of storage allocated. It's using EBS storage, and has, let's see, we can look here. So 36 CPUs. So it is a moderately powerful VM, and it's holding 1 trillion rows of data. Let's go look at that real quickly. So I'm in the ClickHouse Play UI, which is a really great feature of ClickHouse. It pops up a web UI. If you haven't used it, this is something you definitely check out. Let's just count the rows in this table. So just to confirm that we've really got that many rows there. So we'll run this query, and oops, here we go. Get our SQL. Okay, so what we see right here is we run this query, and we have, that turns out you can kind of mentally put commas in there. That's slightly over 1 trillion rows of data. So let's do some things on it. This is sensor data, and we'll show you the schema, but I just want to, it's basically temperature readings on sensors. It is a sample data set that we've generated that was originally taken, from a, here, let's get this query. One second. All right. Sorry, having some cut and paste problems here. All right, there we go. Let's just run a query where we're basically asking for the maximum temperature that was ever recorded on a temperature that, or sensor that had ID 2555. So and so what this did was it basically scanned all the data for that particular sensor ID from within the trillion rows or so. It was able to locate the relevant rows. There's multiple, as we'll see, there are different types of messages that are associated with these readings. This one is called reading, and it means it's temperature. And it got this back in 0.4 of a second. That's pretty fast. So we might want to know something a little bit more interesting, which is on what day did it actually get that that temperature. So let's have a look at that. So we'll go get our query, and here we're going to go again, once again, looking for the maximum temperature, and then use a really interesting argument that we'll talk about a little bit, that a ClickHouse can actually pull associated data from the row that had that maximum temperature. Let's run that. And in this case, it's about 0.8 of a second. It's slower because we're actually scanning the same data, and we're pulling along a little bit more information along with it. So we're pulling this information here that allows us to find out what the actual date was. So that makes the query a bit slower. And whenever we see things go slower on ClickHouse, we think, well, can we make it faster? And in fact, with ClickHouse, there's a very, very powerful way. If you have queries that you run commonly that you'd really like to optimize the measurements, you can use what's called a materialized view. And I have one which rolls up that temperature data to be to actually just the daily readings. And so if I want to find, what day that we had this high temperature, I'm going to go ahead and run this, and basically same data comes back. It's the same day, but it ran it in 12 milliseconds. So this is really fast. And in fact, as we'll see later in this presentation, I didn't use a particularly efficient form of this table, but ClickHouse is just incredibly fast on these kinds of data. And again, this is drawing off data that comes out of 1,000,000,000,000 rows. So I hope this sort of gives you a sense of the power of ClickHouse. Once again, not a particularly powerful, powerful uh, VM that we're using, but we're able to get these very, very powerful or very, very quick uh, results in queries. Let's see how we did it. So we'll go ahead and push this away and get back to the discussion. So what we're going to be looking at in the rest of this presentation is how to enable fast, cost-efficient end user access to trillion row data sets. So this is a key thing, because a lot of times people will frame the problem as, hey, I just need aggregates, like daily aggregates or something like that, or hourly numbers. We're actually going to be focused on enabling people to find the actual source data and then to ask questions directly on it. And so when we say fast, we mean consistent sub-second response, and we want it to scale linearly with resources. This is a really important point, that it means that as your data set gets larger, as you add more tenants, as you have longer time stretches of data, you can just add more resources and preserve your response time. Second thing is, we want to deliver the query results at costs that are low and predictable. So with these large data sets, they're often used for multi-tenant systems. If you have sort of random, we call this serverless mystery billing, where you don't really know how long things are going to take to run, and you also don't know how much they're necessarily going to cost. That's very difficult to use for many use cases. And then finally, trillion row data sets, they're just many types of these. Market tick data is a pretty uh, is a popular one. CDN telemetry. There are countless data sets that are very large and fit in well into SQL data warehouses. So one of the things to talk about is why we do focus on source data access, and this picture sort of shows you that why this is important. Let's say we have a question, like we're seeing temperature sensors fail intermittently, but we don't know why. So what we're going to do is we're going to start going in and doing very quick explorative queries on this sensor data, where we may look at particular sensors, we may look at particular regions, we may look at particular stretches of time to try and find patterns that enable us to zero in on the root cause. And if we can do this effectively, we might find that, hey, there was a bad firmware upgrade. That's the common factor and it was, a bad firmware upgrade that affected certain devices in certain locations. Um, Bang, we solved the problem. That's why you want this access to the data, and you want to be able to do these queries very, very fast. It's not good enough, and by fast, as we say, sub-second or better. So with ClickHouse, uh, we as a community have a lot of experience now about how to build data sets that can solve these problems. And here's some of the basic principles that we follow when we're either building these systems ourselves or advising people how to do it. So first one is, you want to reduce the queries to a single scan. Why is that? Well, if it's a single scan, it's linear. And so if you're just jamming through some amount of data, no matter how how much it is, your response time is going to tend to be pretty predictable. It's just a factor of how much data are you scanning. Then another thing you want to do, another basic principle, is make that data as small as possible so you reduce I/O. Third thing you could do is parallelize the query. So, once we've got it as small as possible and we've got basically a linear process, we can now parallelize it, and ClickHouse is very good at this. Fourth thing we can do is we can lean on aggregation. And this is one of the secret powers of ClickHouse, and we'll show you how to use it in a way that, for example, allows you to avoid doing joins. And then finally, we'll index information using materialized views. So I showed you an example in this in this, in the demo of how I was pre-aggregating, but we can also use materialized views to find interesting events inside the data set. And we'll show you an example of that. So the key here then is that kind of brings these things together is that in these very large data sets, the closer you get to having a big fact table, the better, the easier it is to achieve your goals of fast, consistent, cost-efficient query. So, and this summarizes what we're going to be looking for is you have a single table, an enormous table in many cases of unaggregated table data. So we're not pre-aggregating. It's just the source data. And we're going to do things like maximize applied CPU, minimize the IO by making things smaller, parallelize the daylights out of it, keep intermediate results in RAM, and this will make the queries run fast and predictably. Now, I want to stress it's fine to have joins. There's no problem having joins, and ClickHouse, contrary to popular belief, actually does joins pretty efficiently. It's just you don't want them to be big. So you want a fact table, and then ideally relatively much smaller tables alongside. ClickHouse is introducing support for large table joins, but they're relatively slow, and they have a problem that in very large data sets, to do them effectively requires moving data. ClickHouse can't do it, and also, or can't do it as efficiently as other databases. And even in those cases, this is relatively slow. So this is basically the system that we're focused on building. And there are many of these out there, and they have really outstanding results. So let's go ahead and dig into basic design. These are design principles that you would apply no matter how big your data set is. So let's have a quick look, first of all, at the ClickHouse server architecture. So if you're familiar with ClickHouse, this is probably old hat to you, but basically ClickHouse has a three-stage process for handling queries. There's query parsing, query interpreter, and then a pipeline which actually executes them. ClickHouse can read data from a couple of different locations. It can use columnar data in block storage that could be either local, or in the case of the demo we have here, we're using elastic block storage on Amazon, which is accessed over SAN. And you can also read data out of object storage. Block storage goes through filters to the OS page cache. So once data are cached, if you've seen blocks before, that makes the IO faster. And then we have a bunch of caches in memory. For example, we store the primary key indexes. We'll talk about what those are in a minute. The blocks, as they're scanned from storage, they're held in memory. If we're doing joins, we're actually going to compute by default compute hash tables, and then we're going to store the intermediate query results. We won't talk a huge amount about memory in this talk, but it's definitely something to think about, and we have other webinars that cover it in detail. So ClickHouse, it has an amazing number of ways to achieve high performance, both in this use case of large data sets, but also many others. So things like codecs, things like compression, things like tiered storage, where we have different types of storage. Everything you can think of that will make a data warehouse run fast, there's a pretty good chance that it is implemented somewhere in ClickHouse. What we're going to do here is focus on a couple of key areas, which include things like compression, use of indexes, sort of correct data types, sort of the basics, as well as some basic parallelization. So let's go ahead and just dig into that. The first thing I'd like to talk about, because it's the first thing you think about when you load data, is to understand the organization of the tables. So ClickHouse uses a standard for large tables. There's a family of tables, table engines, if you will. These are access methods for data, called merge tree. This is the standard table for large amounts of data. There's also replicated merge tree. And a number of other variants that we won't go into here. But the basic idea behind merge tree is it breaks up your data into parts. So that's what these are. These are chunks of data that then can be accessed independently in a parallel fashion. And then within each part, there's a very particular structure that includes a primary key index. So it's a what we call a sparse index that has entries for to allow you to uh, to access particular rows within the data. The columns, instead of storing things in column format, this is a column store. So for each column, you'll have typically a pair of files. It depends somewhat on what version you're using, whether you have nulls, things like that. But the basic idea is you have a pair of files for each of these columns. One of the files is basically a bunch of offsets into the actual data which is stored in the other file. And so, for example, if you're looking for something that happened on a particular day and your index is correctly set up, it will enable you to very efficiently decide which blocks to read out of these columns. ClickHouse also has indexes, so skip indexes. These are two examples: min-max, Bloom filter indexes. These are things that you can use to help ClickHouse decide whether it needs to read a particular block or not. We'll show an example of that in a minute. So the reason this is important is getting that structure on disk correct means that you're going to get a lot more efficient IO if you kind of do things the ClickHouse way. So in this particular example, and when I started to put this data set together, I just started out with creating an unoptimized table. And then because this is a sample, I use generated data. So it was actually generated within ClickHouse. But what I do is I create a table and I just, it doesn't contain all the data that I'm actually interested in, but it contains enough that I can begin to understand what it's going to look like and what the size is going to be in storage. But it has suboptimal data types. It doesn't use codecs. We'll show examples of those in a minute. It doesn't bother to partition the table. This just tells this partition by tuple basically tells ClickHouse, hey, partition it any way you want, kind of random, and don't bother about ordering. Just throw the rows in the order that they arrive. This is a terrible table, but the thing is that it will work no matter what your data looks like. You can get the data in, start to play around with it, and understand how to make it better. So what we'll do then is we'll populate data into that, and eventually, by playing around with it, we can get to a better experimental table with much lower IO costs. So here's an example of where you might go with this data set, and in fact, mirrors the process that I went through in setting up this sample. So in this case, what I'm doing is optimizing the data types. So I'm making them as small as possible. I'm using codecs where possible. So a codec is a function that squeezes the air out of the data before it gets handed over to compression. Double delta is a great example of a codec. Instead of storing the integer, the int32 of sensor ID, it stores not the change between successive values, but the change on the change. So for values that like integer values that are slowly increasing in a monotonic fashion, this is extremely efficient encoding. And then I squeeze even more air out of it using ZSDD compression. That's not default in ClickHouse. ClickHouse can do LZ4, but ZSDD is particularly good. We'll squeeze more data out of this column typically. Other things we can do, we can a date. We have a time value here. Dates, of course, can be computed trivially from time. So we have what's called an alias column. So instead of storing it, we just say, hey, this is something you can compute. We use time-based partitioning. That's very, very common in ClickHouse in large data sets. So this will now cause our data to be broken up into nice blocks that are based on, in this case, month. And then finally, we have an order by, which is designed to give us the best, sort of optimal location for data when we're doing queries. And if you get this right, it not only makes your queries faster, but it does things like also enables you to use less space because good orderings tend to help with compression. So we play around with this, and what we can do, and this is the first part of the schema design, is we see that we have this on disk, substantially different on disk data sizes. And given that we're going to store 1 trillion rows, we want to get one that's pretty efficient. So we have kind of a baby bear and a mama bear and a papa bear size. The best one, let's say the papa bear size is over on the right. That's ZSDD compression. That gives us the smallest amount of data, but ZSDD is a little bit more expensive. So in fact, what I ended up doing in this was I went with optimized data types codecs, but I used LZ4 compression. And what I get here is 1.34 bytes per row, which is really great because it means that this data set, this sample data set, will fit on a single VM. So getting this storage right and well optimized is a really important step for any data set, but when they're big, it's particularly critical. We can also practice, look at the effects of parallelization and understand, whether we can add more CPUs. This helps us size VMs. This here shows the basic uh, steps that we go through when we're processing a query with parallelization. And the key things to notice here is we have that parse and plan step. Those are the first two steps. And then we actually run the query. And most of the time, typically, is going to be, well, in many cases, is going to be a vectorized scan. So we're going to split this up into some number of farm this out to some number of threads. They're going to be jamming through storage as quickly as possible. They will hold intermediate results in memory. And then at the end, they will merge those results, sort them if it's required, and hand them back. So that's the query model. If you get this right, the scaling is excellent. So we can now test the scaling. What this is right here is a query on just a billion rows of this sample data. The query itself is not important, but what's interesting is that over here, we have a graph that shows the number of threads. We can set that with this max threads parameter, which is a setting that ClickHouse allows that will control the number of threads that will be applied. And what we can see here is we actually get linear scaling up to 16 threads, and then it drops off a little bit at 32. This is a log linear graph, so, and that's to show that enables us to see the scaling. So ClickHouse has excellent scaling if you put things into a single table like this and make sure that you're asking questions that can be parallelize well. So these are basic things we do to get started. At this point, we have sort of a general sense of, sort of how to store the data and how to query it and the scaling that we can expect. Let's talk a little bit about ingesting data into large tables and show a couple techniques that people use. So here we have one thing that's really important is that as we're thinking about the final schema, we talked about having having a single table, which means that if we have interesting data, we're likely to have multiple entity types. And what we're going to do is store them in a single table. So, and this is all because we're trying to avoid large table joins. They're basically an anti-pattern. So here's the schema of the data that we're reading, and these are different types of events that may be arriving related to a particular sensor ID. So let's just go ahead and look at how we might store that. So one really interesting thing that that many systems do is they don't just store the raw data or the actual data in columns the way I showed you a minute or two ago. They will include the source data as well. What's the reason for this? Well, it's simple. As you have these very large data sets, you may have event types that you don't really know what questions you want to ask about them. So what you can do is if you have enough space, you can just go ahead and store the JSON data. And if you apply compression on it, you can sort of squeeze most of the air out of it. In this particular case, this type of event you see right here compresses by about 96% in ZSDD. So you still pay the cost of the additional, the additional columns, but they're very small, as we just saw. But even storing the source data as, sort of unformatted is also relatively efficient. One thing you might be wondering about when you see this, because we're actually going to store this as a string, is why don't we use the new JSON data type, which was just introduced in ClickHouse? And for that, the answer is simple. One is it's still experimental. And for very large data sets, if you want them to run right now, you also want to, you just want to store it as strings. That's been done for years. It works really well. But there's another issue, which that data type still does not handle multiple uh, uh, entity types. So when the when the JSON schema changes, it may not handle it properly in their cases where the data can get sort of munged together. So we don't recommend doing that yet. Uh, we store it as strings. And in fact, what you get is a schema that looks like the following, and this is pretty close to our final schema. So we have which is basically what you saw before. We're going to introduce a discriminator column because we have multiple event types. So we'll want to tell which kind of event we're dealing with, a reading, a restart, or an error. Um, there's the temperature because that's the main thing we're interested in, error message if we get one. And then the JSON data here is just a string default. And there's an error here that actually should be, that should have a codec to apply ZSTD compression on it. So, and then, sort of a reasonable sorting by ordering by message type and partition by time. So when you do this, that gets you that basically gets your, you can start loading the data. I'll just very briefly say that there are many ways to load data. One common one in this particular type of case is you may have the sensor data coming in JSON. You can read it into an ETL table, just sort of a dummy table. We use the null engine. And then because you're going to have to do some transformation on it to pull the data out and put it into columns, we use a materialized view for that. And so as the data is inserted into this initial table, what that does is it causes the materialized data to materialized view to fire, and then the select from that will put the data into the final destination. This is a very common pattern. We've covered this in other webinars around JSON. You can look it up. So one of the things that I wanted to talk about, though, is how you can get those columns out later. And it turns out this is something where even for large data sets, ClickHouse makes this very easy. At any time you want, you can alter a table and you can add columns. The operation is instant. So what we do here is we're going to pull out the firmware data and we're going to make it a column. And so what we do is we add the column, if it doesn't exist yet, call it firmware, it's a string, and then we give it a default value, which is, and you can see this JSON extract function that pulls it out of the JSON data or the JSON column. It's looking for a key or for a data that the value of the key firmware. And that completes instantly. And at that point, any query you do, you can reference the column, but the data isn't actually in it. It will simply run this function to go ahead and compute it. We can force the data to be materialized by using this alter table. And what this will do is rewrite that one column, and it will you then have the actual properly materialized data. So there's one other thing that's kind of interesting, and this is kind of an advanced trick that I have seen used successfully, is you can query the column, but you can of course query the JSON data directly. You can even index it. And here's an example. So one of the tricks that I've seen used successfully is to actually take that JSON data type, which is just a bunch of JSON, and actually add a Bloom filter index on it. So this is called a token Bloom filter index, and it basically tokenizes the data in that JSON, and then it applies an index. And the settings here are tricky. This is the first setting is the size, and then the second one is the number of functions. You have to play around with this a little bit to get the tuning right. But once you do that, you can actually run queries very efficiently directly on the JSON. And here's an example if we're just counting matches for a particular firmware type. you see the query on the column, you see the query on the directly on the JSON. The performance difference is actually not that bad. Uh, so this is a test that shows the effect of, if you tune the bloom filters, so that's the orange brown one. In the middle, the bloom filter actually performs pretty well, almost as well as the column. So this is kind of a cool trick that, again, you can use in large data sets that allows you to do needle in the haystack searches and find data. So let's get to the final part to talk about some unique ClickHouse tricks for large data sets. So many of the things, for example, parallelization, are things that, hey, Snowflake does that. But ClickHouse has some really interesting features that are particularly well suited for these very large data sets. So let's look at those. So returning to our basic question about how do we make queries fast on these large data sets, the key here is to create queries that work on a single scan without large table joins. You just want to have a linear scan, and you want to just do one. And let's just have a look then at some of the ways that we can do it. So the first thing is, well, how would we actually do that? What tools do we have available? And the key, the tool that we have in ClickHouse that we can lean on is aggregation. Because aggregation, as it turns out, has a bunch of really favorable performance properties. One, and this is an example here, you can look at it. This is how averages are computed inside ClickHouse. It's it First of all, there's no need to move the data. You just scan the data once, and you're sort of keeping counts of, sort of sums and counts as you go down each thread. Second thing is that same algorithm parallelizes extremely well, not only across cores, but across machines and even across time, in the sense that you can compute things up to a point. You can then and store the results, and you can add more to it later, and then you still get a correct result. And that's the third thing, is that these intermediate results are reusable. So aggregation is a tremendously powerful feature of ClickHouse, and in fact, it is the fundamental mechanism for getting information out in a hurry that's useful to human beings. So how can we use it? Well, how do we do a query over all entities? So normally, if you're thinking in traditional SQL, you would end up to a query on each of the entities, and then you would join them together. In this case, what we're looking for is trying to get monthly stats on all our on a particular sensor. So, like what happened in January, March, how many readings, how many restarts, what were the minimum values, minimum, average, maximum values. You probably have to use like an auto join in many databases. ClickHouse has this incredibly cool feature called conditional aggregation, which other databases have, but ClickHouse means something slightly different. You have this what's called an if combinator, and basically what it means is we're going to do a count if this condition is matched. So here we go. What we have is, if it's a reading, we're going to count it in under column readings. If the message type or the event type is a restart, we'll count it as a restart. And then we have some other things that we're looking at. I could have put if combinators on them as well, but I just left them as they are, so the results are slightly off. But the point is, you can do this, and it's incredibly fast. It's a single scan. We don't have to do auto join. We don't have to move data. It completely gets around this problem of combining different data from different types. What's really interesting is, since we're kind of doing a join, one of the other things you can ask is, can we do this more generally? Can we think about joins, and how would we handle them? And here's an example of a join that you might need to do, which is to join restarts with temperature readings. Let's say that you suspect, or you're interested in, what happens after a device restarts. What do the temperature readings look like? So what we're going to do here is we're going to have a join key, that's sensor ID, and then we're basically going to filter it so that we look at it after, over a bounded period of time. So in a traditional database, this is what you would, what it would look like. You'd have the restart times, you'd have the temperature readings, you'd join on the sensor ID, filter appropriately, and then you could get temperatures after restart. And in fact, you could even compute this field uptime, which is the amount of time that these sensors have been up since their last restart. You can do this because you've joined the data. So let's see how to do this in ClickHouse. Well, first we'll start with a picture. So because we're going to use aggregation for this, and instead of a join key, we're going to use the group by key, which is your fundamental way of pulling information together. And what ClickHouse can do is, so we have the different message types. So the actually, I don't show the message. One is the restart. That's the first one. The second one is the readings. And what we're going to do is group them. So we can get we group by the sensor ID. That's our key. We're going to, 1 second, please. Pardon me, I was getting a background phone noise. So we're going to group by the sensor ID. We can pick up the restart time because whichever one we see inside this inside this period of time. What's really interesting though is ClickHouse can actually collect this information into arrays. So the reading, the time that it did the reading, and the time that it and the temperature that was associated with that reading, there's a special aggregate function that ClickHouse can do to group array values in the order that they arrive. And then there is a feature in ClickHouse called array join, which will pivot the data along the values of these arrays so that we can basically reconstruct a table that looks like the following. So we get the sensor ID, we see the time, we see the temperature, we see the uptime. This is all done using aggregation. So, and here's the code. And I think it's fair to say that this code is not everybody's cup of tea. You may look on this in horror. This is easy for me to say this, that I can do this. I actually teach a class on arrays, but the point is that ClickHouse allows you to do this. So the code is complicated. In this particular case, we use arrays, but it does work. And let me just demonstrate that, because we can go back to our demo. Whoops. 1 second here. All right. So let's just run that query just to show that this really does collect the data that we expect. So I'm going to grab that code and we're going to put it in here, and there it is. So we have our arrays, we're basically getting the sensor, the time that the reading was done, the temperature. Oops, we got reading time twice. Let's remove that. Go ahead and run this query. And there it is. So we actually have done what effectively amounts to a join, where we see sensor ID 2555. We see the reading times. They're offset by a minute at a time. We can see that we've joined on the restart time, so we're actually computing the time since the last restart, which is the uptime. And there's the temperatures. So this is, I'm going into detail about this because I have to say that when I learned this trick, which came from one of our users, it's one of the coolest SQL tricks I've ever seen. So, and it's something that is very powerful and helps to solve this problem of joining data from a single table. Okay, so let's look at one final thing, which is indexing data. So as we get these very large tables, we can ask questions like, hey, when was the last restart on sensor 236 to feed into a query like what I just showed you. This is a traditional way of getting this in SQL databases. We have an in clause with a subquery. Some databases have real difficulty doing this. ClickHouse has a very neat feature where the in clause can return multiple columns. But even with that, this type of query where you just on the fly say, hey, when was the last restart on sensor 236, this can become very expensive to compute. And if you do it often, it's going to make things very slow. So once again, this kind of problem of finding the last restart, it's an aggregation task. So and basically we can think of this again as using the sensor ID as the key that we're going to use that as the group by key. And now we're going to look for the maximum value of, sort of that we see in an event that is of type restart. And we're going to capture the matching, we can capture as many matching values as we want. In this case, we're just going to pull in the message type. Um, but this is basically allows us to construct what's called a last point query or excuse me, a last point index. And so here and the way that that we could do this through materialized views, and the way that they work is a materialized view is like a trigger. And so we're going to set one up. So when a block lands in the source table, it will automatically run a query like the following over it. And then it will stick the result in a materialized view target table. And we're going to use the aggregating merge tree table engine. We've covered this in other, in many other webinars and blog articles, but this will basically allow us to capture these restart times automatically in a much smaller table. What does it look like? This is the code for the materialized view. So here's the last restart. This is the table, the target table. There's a materialized view that feeds that table. So every time new data hits our source table, it will get read in. And basically we'll be able to get that answer much faster. Now, in this particular example, I'm just partitioning by tuple or tuple, if you will. That's a kind of dubious choice for a couple of reasons, but I wasn't paying a lot of attention to this. As it happens, as you saw in the query I did through when I was querying the materialized view, that was the third demo query. ClickHouse is still exceedingly fast. And one of the big reasons for that is when you construct these materialized views, they're vastly smaller. So this is an example that shows the storage size. It compared that materialized view that we're using previously. And that materialized view is only 3 gigs compared to over a terabyte of data in the source table. So it's, sort of many times smaller. The other thing that's kind of interesting is it has a smaller number of parts, and this is an example of why the tuple not correctly partitioning that materialized view could bite you. And one of the reasons is that as the data is being added from from the source table, when blocks are inserted, it will then just get randomly thrown into different partitions, and it causes ClickHouse to rewrite the data. It's also somewhat less efficient on queries. It's better if you partition things properly so the data is located in longer sections. But as you saw from that demo, it came back in 14 milliseconds. Sometimes it just doesn't matter. ClickHouse is so fast. So this is an example of where you can kind of get stuff wrong, but ClickHouse still gives good performance. Okay, so those are basically, this is a really deep subject, and we've just scratched the surface. Let me talk about a few other things that are like sort of some basic learnings from this, as well as some things you might want to look at to build your own tables. So first, as we build these, using a single large table to hold all entities is not bad. I mean, this is not a question of can we do joins. It's it's not a question of limitations of ClickHouse. The question is, how do we make this query behavior become linear? And the way to do that is to put it in a single table. And the second thing is to make good implementation choices. ClickHouse is a great database, but you have to do some work to make sure that your schema is correctly defined and that you're using features like data types, codecs, compression, partitioning, order by, that you're using those most efficiently. If you want to be flexible and you have space, include the source data. Many people do that. And then you can materialize out the columns, or at least have it available to query if you change your mind. Once you load data sets like this, it is really hard to change them. In this particular example, I generated the data within ClickHouse itself. It still took 4 hours to load 1 trillion rows. If you're reading it from some other location, you can imagine just how hard it would be to update the data, and if you realized you missed something. And then finally, aggregation is the secret ClickHouse power. And I hope it is a little weird when you first use it for these additional, uh, but these additional things like the if combinators, the ability to simulate joins, the ability to use materialized views. These are features which are really the things that allow ClickHouse to be incredibly fast and beat just about all comers. If you use them, you'll be happy. And the reward is linear scaling, cost efficient, good cost efficiency, and of course, happy users because they can actually see raw data and get useful problems solved. Some other things that you might think about, obviously sharding and replication. Some of you probably thought I was going to talk about that, but it just happens that with ClickHouse, if you set it up correctly, it's no problem doing 1,000,000,000,000 rows on a single VM. Uh, Tiered storage and object storage. Probably the most interesting topic is to really to really think about is how to save memory. We didn't touch on that because it's a deep topic and very use case specific, but one of the common things that we look at is that as we're building these large queries, since they're holding results in memory, we will often use approximation techniques, including sampling, as well as what are called approximate uniques. So uniques are when you're doing things like counting the number of unique visitors to a website over a period of time, or the number of unique trades or unique GitHub contributors, something like that. Those aggregates can be very expensive, both in terms of processing time and memory. ClickHouse has lower cost versions of them, and we constantly use them to make things run faster. There's documentation for all of this. There's obviously the ClickHouse official documentation, which you can go to, which is your basic reference. We have a number of things like the Altinity blog. We've talked about these features. YouTube channel, we have lots of videos like where this one is going to land. And then we have the knowledge base. So this is just a gold mine of just raw data that comes out of our support. And we have about 200 customers, actually more now, that we're helping. And every time we find something interesting, our support engineers just toss it in there. I use it constantly. And in fact, a number of things in this talk came out of the knowledge base. And then of course, there's meetups. Other people have blogs and external resources. If you search, you will find. And that's it. We are within 5 minutes, but I hope this has been helpful, and I would be delighted to answer any questions that you have about this. And I'll hold it open. Please go ahead, just post the questions into the Q&A box or into the chat, and I will answer as many as I can before we run out of time. Okay, don't be shy. So, let me say something. If you want to contact us about this and talk about some of these topics in greater detail, we are available at our website, altinity.com. You can just go ahead and contact us, and you will find, we can set up a meeting, or you can join us in our Slack workspace. There's just a bunch of ways to talk to us and dig into these issues. Not a question. Robert is not using his Ubuntu box today. So this is okay. Here's a really great question. Ubuntu box. Hey, let me put in yes, I'm not using Ubuntu. What I am using here today is I've kind of fallen in love with Windows and the Windows subsystem for Linux, WSL. It's actually really good. So I'm thinking of using it for ClickHouse development. So, and it's really good Linux support. Okay, here's a question. Do you still recommend using a single fact table if it results in a lot of duplication of some data? The answer is yes. And in fact, this is generally something that we do in ClickHouse data warehouses because the compression is so, and I think to expand this, I'm guessing that you're thinking like, hey, maybe we use a snowflake schema, which will allow us to just, have the data spread out across multiple tables, and thereby save storage. Well, it turns out that ClickHouse is sufficiently efficient on compression, uh, including things like codecs, being able to control sort orders, that there's usually not that much storage cost to adding more data. You saw that with this data that I was playing around with, I was able to reduce an 8-column table to well, leaving out the JSON, I was able to reduce it to about a little over a byte, which is just really amazing. So so you can add a lot of columns, and ClickHouse is particularly efficient if the columns are sparse. So that's not a problem. Uh, they compress really well, and ClickHouse can read over or skip things. So yes, I do recommend using a single fact table until you find you have an issue. The other thing about this is that there are many cases where you just want to have what was the then current value of tables that you might otherwise join on. So again, having a large fact table with a lot of columns solves that problem. So that's a definite yes. Okay, question answered. I'll give you 30 more seconds. Yeah, the group by equals self join table. Yes, this is uh, okay. The filter out data using has any in arrays efficiently. That's okay. So here's a question: how to filter out data using has any in arrays efficiently? That's a really good question, and I would actually have to play around with the code with that a little bit. I don't know if other people have ideas on this. You can use array map functions. One thing I will say about arrays is that they use memory. So there's like with many things, using these, uh, using these, sort of using arrays means that there's no free lunch, right? If you're going to do a join, you're going to store stuff in memory. If you aggregate using arrays, of course, you're going to drag those arrays around until they can get merged. So you could definitely try array map. That would be uh, something. And if you're seeing particular performance problems, if it would be great to see exactly what they are, file them as a ClickHouse issue and bring them to our attention, and we'd be happy to look at them. Yeah, here's a comment. Using Bloom filters did not work for us. That is a very common experience on Bloom filters. And what I recommend is we have a Bloom filter. Bloom filters are really hard to tune. And the reason is that you actually have to set the index size, like the size of the index you permit per block. You have to set the number of functions that you use to calculate the hashes. And you you have to play around with it. It does not work if you have a lot of low cardinality data. Like if you search on the word a Bloom filter is not going to help you much. And it, so where I've seen this used successfully is people searching on things like transaction IDs. So imagine you have an e-commerce site, you have transaction IDs. That's by definition a high cardinality uh, uh, piece of data. And what you're looking at is, hey, find all the things that belong to this transaction. Bloom filters work great for that. So we see when they're correctly set up, we see them knocking out 90, 95, 97% of the blocks. But again, it really depends on your data. It will not work if you have JSON data that's very tangled with many, with many different uh, types of uh, very tangled data with a lot of overlapping keys. Okay, not a question, but a comment. Probably would be good to add more examples. Preware does helpful magic. And yes, this is a really great point. Thank you. So preware is a very powerful feature in uh, uh, preware is a super is basically allows you to use columns as kind of rough and ready indexes. So what will happen is that, and ClickHouse, if you're filtering on a column that's not in the primary key index, it will automatically try and do a scan to see if it can figure out which blocks you need to touch before it scans the rest of the blocks. So So, but on the other hand, as this correctly points out, uh, it's it only works in some cases, and sometimes you need to turn it off to for complex queries, you'll actually pay more if you do pre-aware. So that's totally, we've had exactly that experience as well. Here's another one. What would you suggest for a low cardinality column? Set indexes, primary key, composite keys. You know what I would do for low cardinality columns? So things like, 0, 1, I would just compress the daylights out of them. Not really worry about trying to skip values. Uh, when the and this is even true with these. Uh, and if you find yourself searching on that, uh, I would put it on high-speed storage. I would go ahead and try and compress the daylights out of it. That'd be the first thing I would think about. You can use set indexes for this. The problem is that if your data are scattered across, like zeros and ones, let's just pick that as a case. If they're scattered randomly across the blocks of data in a column, even with a set index that says, hey, which columns contain this value, every column will contain every value. So it will be worthless. It's just faster to scan. So in that case, then the important thing is just make sure that you've compressed the daylights out of it. Good. We're a little over time. These have been great questions. Thank you so much. I'm just checking to see if there were other columns or other questions. Once again, I hope this was useful. If you have suggestions for what we could put into this, we'd love to hear more about this. We tend to do more talks on this topic. And if you want to learn more, talk directly with us. Contact us at altinity.com, join our Slack channel, and we'd be happy to talk to you. So with that, thank you very much. I wish you a great day.